Hi, Jasmina. Sorry, I don't have my ears in yet. Hi, Jasmina. How you doing? You're not unmuted yet.
Hi. Hi, I'm good. How are you?
Doing fine. Do you remember how far we got? I thought we got to the end of this chapter. Do you remember?
Let me check in my notes what the last thing I wrote down was. The last thing I wrote down was the values of MS.
Okay. Okay. Good enough.
Right. Yeah, I think it
I'll
was
go
that.
through. I'll go through a little bit of review, and it's not much review that's necessary, but I will go through a little bit of review. Bottom line,
All right.
we have. I'm hoping to get through everything I need to get through today, and I should. Okay. So bottom line, we will have a test on Tuesday. Crickets.
I
here.
have two questions. I have a few questions on both quizzes,
Okay.
and then
Ian,
on the
can we wait?
PowerPoint.
Ian,
Yeah.
are you available after class?
Yep.
Then I will be happy to go over them with you then, okay?
Okay.
The one
And will you be going over all of Chapter 9's PowerPoint today?
it's chapter 9's PowerPoint is not that long, yes.
Okay.
I'm gonna do my utmost, okay? What I don't,
Okay.
I haven't written the test yet, so what I don't cover will not be on the test, okay? Fair enough?
Yes. Well, those questions will be written like how you write the quiz questions, right?
Kind of
Or
sort
will
of.
they
Yeah.
be? Or
Yeah,
will they be
I'm
like?
gonna ask you, you can fairly well expect, like on the quiz, I will give you 4 quantum numbers and ask you what the element is. Or
Okay.
I could ask you, all right, the last electron going into iron has what 4 quantum numbers, according to my rules. Okay, Ian?
Okay. It won't be set up like the mastering with how that's worded.
I'm sorry?
With how the mastering's worded with the homework, will it be like that at all?
No, it'll be my wording, like the quizzes.
Okay, cool.
All right. Who else is in here? I know Ian and Jasmine are in here. Somebody else snuck in here.
Hey, Professor.
Hi, Gabe. How you doing?
I'm hanging in there. How about
All
you?
right. Any questions?
No.
All right. The good news is, as I was saying, Jasmine and Ian, the test will be on Tuesday. I should be able to get through the PowerPoints for chapter 9. Chapter 9 should be fairly easy. Basically, you're going to be responsible for what I cover. If I don't get to periodic trends, I don't get to it. Okay? Fair enough?
Yeah, sounds good.
All right. And let's see. That should be it. Okay. We left off with the MS number last time. And the MS number was the one that indicates the spin. And if it's a positive, it's going in a clockwise direction. Negative, it's going in a counterclockwise direction. And what that means is in relation to any magnetic field that the electron may be around. Because one of the things you have to understand is if you have something with a charge that has spin on it, you have a current. Okay, and you have something with a charge and a spin has a magnetic field to it. And it depends upon if that has a magnetic field and you put it in the right orientation of another magnet, then what's going to happen is it adds to the energy. If you put it into a field where it's kind of going counterintuitive, it will detract from that energy. And so that's why you get this different energy level for the spin of the electron. Now, quickly, we're just going to review principal quantum number n. It can be any value from 1 pretty much up to 7 because the periodic table doesn't go beyond the shell 7. Okay, so it's 1, 2, 3, 4, 5, 6, 7. The value of L is going to be, and it can have values from n-1 down to 0. Okay, so if I have an n of 2, I can have an L value of 1 or 0. All right. If I have an n of 4, I can have an L value of 3, 2, 1, or 0. The other thing you need to know is that the L corresponds with what the letter designations that you learn from introduction. 0 is the s orbital, 1 is the p, 2 is the d, 3 is the f. And basically, what this indicates is the shape of the probability of the electron. S's are spherical, P's are bilobed, D's are have 4 lobes in them, or they have the 2-lobe thing with the donut. And F's, I'm not even going to begin to describe F's. If you're that curious, go back to the slide and look. Obviously, I'm not going to be testing on you on the shape of the F orbital. All right. Okay. The next quantum number is m sub L, and m sub L values can be minus L value. M sub L numbers can be minus L values through 0 to plus L values. So if my L is D, my M sub L can be -2, -1, 0, +1, +2. And what the M sub L stands for is it is the orientation, the spatial orientation. It is one of those pictures, those probability pictures that you saw. It's whichever orbital it gets placed in. The fourth one, M sub S, can have values of only +1/2 or -1/2. And it depicts the spin of the electrons. Okay, we good with that? Now, another thing you have to understand, even though in a couple minutes I'm going to designate something, you have to understand the M sub L values. If I have all things being equal, then the electron can go, if I have a p orbital, I have 3 suborbitals that are equal in energy. If I have a electron, the first electron going into the p orbitals, it doesn't matter really which one it goes into. They're all the same. I'm going to designate them later on as to what I want you to fill in. But really and truly, there is no difference between whether something goes into the -1 orbital, the 0 orbital, or the +1 orbital. There's no difference. And if you have an electron in the -1 orbital and another one going in, it doesn't matter whether it goes into the 0 or the 1. They are both the same energy. Again, I am going to designate in a few minutes what I want you to call the quantum number for it going into the last electron of the element. And I apologize for the phone. Sorry, my wife's coming in to fix it. Say hello to my wife. Nobody said hello to my wife?
Hello.
All right. Now, so giving that information to you about the quantum numbers, Gabe, is A possibility? Can A be a possible set of the quantum numbers?
Yes.
Okay, look at L.
Yeah.
All right?
Oh, wait. Oh, yeah, I can. Wait a second.
Remember, L values go from n-1 to 0.
Oh, so A can't be.
A cannot be a set of quantum numbers because if the principal quantum number is 1, then the only thing L can be is 0. Does that make sense to you, Gabe?
Yeah.
Okay, Jasmina, is it possible that B could be a set?
Yes.
Yes, it is, because n can be any value, basically an integer from 1 to 7. 2 qualifies. The L value can be anything, n minus 1 to 0. So n minus 1 would be 1 or 0. That qualifies. All right. The magnetic orbital can be minus L to plus L through 0. That qualifies. Now, the electronic spin can be a plus or minus 1/2. Good. All right. So, Ian, is it possible, or is C a possible set of quantum numbers? I see you out there, Ian, and you're unmuted.
I had my mic muted and I was talking the whole time. Yes, C can be possible. L is n minus 1 and m of L is negative of L.
And the electronic spin. All right.
That's always negative 1/2 or
All right.
positive 1/2.
Now you have to understand what these numbers represent. These numbers represent solutions to the Schrodinger equation. Okay. So from what you remember back from intro, remember when the principal number is 2, I can only have the second shell. If you've got your periodic tables open, look down to the second level. Unfortunately, I don't have one available to me right now. Do you have a periodic table, guys?
Yes.
All right, look at the second level. What type of electrons can you have in terms of sp, d, and f?
S and P.
S and P. In other words, L can be 1 or L can be 0, correct?
Yes.
So that's what that means, guys. If I have a principal of 2, that means I can only have p and s orbitals. If my principal is 3, I can have d, s, and p. If my principal number is 4, I can have f, d, s, and p. Does that make sense, guys?
Yeah.
Thank you, Jasmina. Okay. Last thing we got to talk about is something called the last thing in this chapter is the Pauli exclusion principle. And basically what Pauli said was, for any electronic system, no 2 electrons can have exactly the same energy. Now remember, all those quantum numbers are different solutions to correct energy levels that the electron can have. So if no 2 electrons can have the same energy level, then what that means is that no 2 electrons can have the same set of identical numbers. No 2 electrons can have the same set of 4 quantum numbers. So when we have something like sodium that has 11 electrons, there are 11 possibilities of quantum numbers. 11 different quantum numbers are set up for sodium. That makes sense, guys?
Yes.
And we have killed another chapter. Now, I don't know if you're going to be happy about this news or unhappy about this news, but right now, we have done the major load of this test is going to be on thermodynamics. That's the math burden for you. The rest of this test is going to be on quantum numbers, quantum theory, and it's going to be on just being able to work theoretical things rather than math things. So some people like math, some people hate math. That's just where this lies. Okay. And there was something else I was going to say, and it just completely just flew out my head. Oh, yes, you are responsible for, I will probably put one discussion question regarding the theory of Heisenberg and Schrodinger. Okay? Fair warning on that.
I'm sorry, can you repeat that? Sorry.
I will probably put one discussion question, in other words, one essay question, in which I will make a question regarding the development of the quantum theory. Okay?
All right, let me just write that down. Development. That's on the test, right?
On the test, yes.
Development of quantum number.
All right, another thing that's going to be fairly comforting to you is a lot of what I'm going to do today is stuff you've already had before. It's review. All right. So we're going to get into today, we're getting into the configurations. We're going to get into electronic configurations. By that, this is the 1s2, 2s2, 2p6, and so on and so forth. Generally, I found that most students like this because it's once they get it, they're easy points on a test. Once you get the whole concept of how to do electron configurations, it's fairly easy to translate that on a test. Same with the orbital diagrams. The orbital diagrams are where you draw the orbitals and then you put the electrons in with either the arrow up or the arrow down. We're going to deal a little bit with, we're going to definitely deal with something that's not on here. We're going to deal with quantum numbers, assigning quantum numbers. And I'm sorry, I forgot to put that in here. Then after that, I guess there should be two S's there. After that, we're going to get into, and I don't want that. Why do computers do what you tell them to do rather than what you want them to do? After that, we're going to get into something called the effective nuclear charge. And we're going to get into a more in-depth looking at the periodic trends. I know we did periodic trends earlier, but this is going to be a more in-depth treatise, okay? Hopefully we'll get to that. All right. Now, we can look at the periodic table and we can use that as a guide for us to do the electron configurations. The period number, the row on the periodic table, that's going to be what the value of n is for the most part. Groups 1 and 2 have the s orbital filled. Groups 13 through 18. These are where the nonmetals begin. It begins with boron through actinide. Those, I'm sorry, through, I'm sorry, I don't even know what's beyond the, sorry, it's that section of the periodic table. That's going to have the P's. The middle part where the staircase goes down, that's going to be where the d orbitals are and the lanthanide and actinides, the two rows on the very bottom, that is where the F's are going to be filled. And it looks basically like this. In a real correct periodic table, you will have the F's are kind of like in between the D's and the P's. It's just hard to have a periodic table if you put the F's where they're supposed to be. So basically they take these two rows and put them down below. First two rows are going to be S's. The last six rows, columns. First two columns are going to be the S's. Last six are going to be the P's. In the periodic table where it goes down, that's where the transition metals are. Those are going to be the D's. And the bottom two rows are going to be where the S's are. Okay? Now, what happens if you get too many electrons on the same energy level? You have minus charges going with minus charges. They don't like it. So what happens is you have more energy when you have more electrons in a suborbital, like the Ds. The Ds have 5 suborbitals in there. P's only have 3. S's only have 1. If you have 5 suborbitals, this means you have a possibility of 10 electrons. Well, that makes this a little more energetically unstable than the S. So literally what happens is if you have the 3 Ds and you have the 4 S's, because this has so many electrons in, the energy levels switch so that you have the S's get filled, the 4 S's get filled before the 3 Ds. Does this kind of like make sense? Did that make sense to you?
Yeah, that makes sense.
All right, so we have to realize that the S's with the higher N number, higher shell, will get filled before the D's with the lower N number. The way you figure out the order of the shells, it's very, very easy. You just draw this chart out. Put 1s, then put 2s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, and so on and so forth up here. Just fill this chart out this way. Then what you do is you draw diagonal arrows. Okay, and you go from the feather end of the arrow to the pointy end of the arrow. So I'm going the first one, I'm filling the 1s first. Then I'm going from the head of the arrow back to the feathers. I'm filling the 2s. Head back to the feathers, 2p, 3s, back to the feathers, 3p, 4s, back to the feathers, 3d, 4p, 5s, back to the feathers, 4d, 5p, 6s, back to the feathers, 4f, 5d, 6p, 7s. Is that making sense to you? I'm sure you were told something like this in the past. Do you remember it?
Yes.
Okay, now every suborbital can hold 2 electrons and only 2 electrons in it. And those 2 electrons are going to have opposite spins. So the electron configuration that we're going to do in a second describes how the electrons are distributed in the various atomic orbitals. The orbital diagram is going to give a graphic depiction of how those electrons are distributed. So if I have hydrogen, I'm going to call my electron configuration. I need to put the N number. I need to put the shell of where those electrons are going in. I need to designate the L number. In other words, the shape of the orbital. So in hydrogen, the 1s gets filled first. Then I have to put a superscript that tells me the number of electrons in that orbital. Does that make sense, guys? We're going to do electron configuration first, then we're going to go and do orbital diagrams. So for hydrogens, my electronic arrangement, there's only 1 electron. It has to go into the first orbital available to it, the lowest energy orbital, which is a principal number of 1. With the S, only 1 electron goes in there. If I was doing the orbital diagram, I would draw a box, or you can just draw a line. And I would put it at the lowest level, label it 1s, put one electron with the arrow going up. So all of my designations are going to have a number designating the energy level, a letter denoting the type of orbital, and the superscript which designates the number of electrons in those orbitals. Okay, I was looking for one of these and I've just found it. So if I'm dealing with cobalt, remember, I have to draw that little diagram with my 1s, 2s, with that little chart to have my little arrows. So if I'm doing an electron configuration of cobalt, this is my 1 level. My 1 level only has s's in it. So I fill that first orbital up first. So I have 1s2. The next one, according to that chart, principal number is 2. I'm filling the s orbitals first. Both of these get filled. So I have 2s2. I go over to the p's. It's still on the second level. 2p6. I go down to the next level. I'm in the third energy level, 3s2. Go over to the p's, 3p6. Now, this is where it gets funky. If you look at that chart, if you look at the chart, we went from 3p to 4s. Now we go down, the 3ds get filled then. So after the 3p's, 4s, there are 2 electrons that go in there. Now, the next one that gets filled is a 3d. I got to count the number of electrons over to where it's cobalt. I put 1, 2, 3, 4, 5, 6, 7. The last number would be 3d7. Questions on it? Old hat? Is this old hat something you guys are familiar with? Or are you confused? I can't see your faces.
Familiar a little bit.
Familiar a little bit, Jasmina? We okay?
I just remember during the quizzes, like there were some in the middle where like if the D was odd, then you would like take away one
Okay.
from the S.
What you're saying, like
Are we gonna get into that?
like for chromium? Am I going to get into why chromium is 4s1, 3d5? Is that what you're asking?
Yeah.
Yes, I will be
Like
getting.
like
Yes,
how to
I will
tell
get into
when
that.
you do that.
I will get into that. Okay. Gabe, you understanding what I'm talking about so far?
Yeah, for the most part.
All right, Gabe, let's do 10. Start with the configuration. You're starting with the 1s's.
Right. It would be 1s2,
Good.
then 2s2. It'd be 3s2.
No, you're
No.
going. You're going from here over to here.
Oh, 2p, right?
2p.
2,
How many
6,
2p6.
2p6, 3s2, 3p6, 4s2, 4p, right? Or 4d, 4d.
Nope. Look at that chart. You didn't draw that chart, did you? This chart, Gabe. You need to do this because if you don't do this, this should be the first thing you do on the test on Tuesday. This should be the first thing that you do is make this thing up. because you know damn well I'm going to put a configuration question on there. So if you
Alright.
do this, okay, you just said you filled up the 4S. You put 4S2, right?
Right.
What's the
Oh,
next
3D. 3D.
Okay.
I just took a picture of it. So.
I'm sorry. Did I mess you?
Oh, no, no, no.
Okay.
No, it helped me.
So we
Alright.
did 3D10,
Right. So it would be 4P, right?
4P,
6. 5S2. 40. Wait, where's the S?
you're doing 4D, you're
Yeah.
doing
Oh,
good.
40, 10. And
And
then 5P2. Because S.
yep, exactly. Exactly. Okay.
Stressful.
Yeah. All right. These are easier. Jasmina, what's the element?
That would be iron.
Iron. Now, you want to know the easy way to do this? You went through each and every one of these, didn't you?
No.
You didn't? You just went to the 3D6?
Yeah.
Okay, guys, the only one that's important in order for you to identify the element is this last one. All you got to do is find out where the 3Ds are. This is the 4S. Right next to it are the 3Ds. So you've located the orbital. Now, once you've located the orbital, all you got to do is pay attention to this number. 1, 2, 3, 4, 5, 6. I am dealing with iron. Good. Good, Jasmina. All right. Gabe,
Yeah.
what element am I dealing with?
You are. Hold on a second.
Again, Gabe,
Mm-hmm.
you see everything up to the last one. Everything up to the last orbital is going to be the same. All you
Okay.
have to pay attention to is the 4P4.
Right.
And you got to find out where the 4Ps are.
Would it be SC?
Selenium. Absolutely. Okay, Ian.
Yes. 48. Oh, yeah, 48. One. It would be, what is that called? Palladium.
Good, you got it. So guys, these are fairly simple, all right? Anybody have any questions on either how to find the element or how to assign the electron configurations? We good with this?
Yes.
All right, on the test, all that's going to be necessary for you to type in, make it easy on yourselves. Just put the principal quantum number, the letter, and don't try and make a subscript. Just put the superscript right after the letter. It would be nice if you put commas in between them. All right. Now, remember, I said in this thing up here, all of the configuration until I get to the last one is the same as the previous one, right? So if we have a way of designating a shell of electrons, then we could save us a whole lot of time from not doing this whole thing out. And we can do that. So if we look at the 4Ps, the 4P6, that's where we're at, correct, guys? If I was going to draw out something, a configuration up to krypton, my configuration would be everything up to and including the 4P6. right? Right?
Yes.
Okay, so all I have to do to shorten this up is to put krypton in brackets. Krypton in brackets means I am designating that my configuration up to krypton is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4ps. That's what krypton in brackets means. So I'm going to find, what I'm going to do is I'm going to find out where my element is. If I'm dealing with gold, I'm going to backtrack. I'm going to go back in my periodic table, and then I'm going to go up a row, and I'm going to find where my noble gas is. I'm going to put that noble gas in brackets. Then what I'm going to do is I'm going to continue the configuration from there. So if I'm dealing with gold, I'm going to put bracket xenon 6s2, 4p14, sorry, 5d, sorry, I got to get my arrow, find my arrow, 5d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 5d, 9. Okay, again, if I'm drawing gold, xenon in brackets, 6s2, 4f14, 3d9. If I'm doing sodium, the noble gas right before it is going to be neon. So I'm going to do neon in brackets, 3s1. Okay, give the name and atomic symbols for the elements that you see here. 3p1 is my last number. 3p1, Jasmina.
Aluminum.
Aluminum. 3d7, Ian. 3d7. Ian, are you muted?
Did you
Ian,
call my name? Sorry,
yes,
I was
I
answering
did.
the phone.
3d7. Sorry about that. 3d7.
3d7 would be cobalt.
Cobalt. And Gabe. 5d6.
XE. Is that right?
No, go ahead. 5d6. I want you to identify the element. Where's the 5d at, Gabe?
Is it down with the LA?
No, that if it was a LA, that would involve an F. F's are down here. D's are going to be somewhere in here. And what you have to remember, Gabe, the D's are going to be one less shell than the S's. Okay? So
Okay.
1s, 2s, 3s, this is 4s. This whole
Mhm.
group is going to be 3D.
Right.
5s, this whole group is going to be 4D.
40.
This is 6s, so this whole group is going to be
5D.
5D. And I believe it was 5D something or other.
It's IR, right?
IR. You are what? 2, 3, 4, 5. I think it was 6. I think it was osmium.
Oh.
What? You have to count this box, Gabe.
Oh,
1, 2, 3, 4, 5, 6.
oh yeah.
So it is osmium. All right. Do I need to do this? Do we need to go through this? I'll be happy to do it. 1 or 2?
We do C.
All right.
What would 5D1 be? Would that be
Yeah.
lanthanum, or would that be?
I believe they go in. It gets funky there, and I won't ask you a 5D1. Okay.
Okay, perfect.
It gets funky because some people say one thing, other people say another thing. I believe LA goes there. Okay, which means everything. If you count the number of boxes here, there are 15 boxes. You don't trust me? Go ahead and count them, Ian. Generally speaking, I see LA put in the 5D1 and AC put in the 6D1, and the Fs follow.
Okay, I see that now.
But part of the thing is you have to understand the only Schrodinger equation that has ever been solved for is hydrogen. They haven't even solved helium's Schrodinger equations because when you put another electron in there, it fusses with things so much that the equations fall apart. So they've only solved it for hydrogen. So in answer to your question, Ian, some people say it's lanthanide that goes in there. Some people say it's Lu, whatever Lu is. All right.
Okay.
And again, I will not ask you a 5D or a 6D1. Fair enough?
Got it. Fair enough.
Okay, somebody wanted gold +3. All right, remember, when we're doing this, we're doing electron configurations, right? Right?
Yes.
Right.
Okay, so if I am dealing with AU +3, does it have 3 less electrons?
Yeah.
Okay, so I'm going to lose this electron, I'm going to lose this one, and I'm going to lose this one. So if I lose 3 electrons, my AU 3+ is going to have the same electron configuration as osmium would. I would do xenon in brackets, 6s2, 4f14, 5d, 1, 2, 3, 4, 5, 6. That makes sense, Jasmina?
Yeah.
All right. If I'm doing sulfur -2, am I adding or am I losing electrons, Jasmina?
Sorry, did you say -2 or +2?
-2.
You're adding electrons.
So if I'm adding them, I'm going over 2. Boom, boom. So S -2 is going to have the same electron configuration as AR. 1s2, 2s2, 3p or 2p6, 3s2, 3p6. Answer your question, Jasmina?
Yeah. Thank you.
Okay. And I can tell I'm not going to get through the periodic trends, which is well enough. Okay. Now, I don't like the way this slide looks, but it's okay. All right. The main thing when you're doing orbital diagrams is you are depicting different energy levels. So as long you can write it this way in a horizontal fashion, if you want, you can write it this way. But you have to understand 1s has less energy than 2s. It's more easily understood if you go from like 1s and then 2s is above it, 2p is above that, 3s, 3p, 4s, 3d, and so on and so forth. But this will work. Okay. You have to understand a couple of things. P's have 3 L values, correct? P has 3 M sub L values. Does that make sense to you?
Yes.
-1, 0, and +1. That means it has the p orbitals have 3 suborbitals in there. Suborbitals can only handle 2 electrons, 1 spin going up, 1 spin going down. Does that make sense to you? Does that make sense, guys?
Yes.
Okay, so what you are going to do is you are going to fill the lowest energy level first. So if I'm dealing with lithium, I have 3 electrons. I draw my 1s orbital, my 1s little box. I put my 2 electrons in there, 1 going up, 1 going down. I still have 1 electron left. I have to go to the next orbital above that, which is 2s, and I put an electron going up. Now, there is another rule we have to establish. When we have degenerate suborbitals, the lowest energy is attained with the number of electrons having the same spin. In other words, when you are filling the orbital diagrams, you want to put them all in spin going up. Spin going up. Is that understood, guys? Spin going up.
Yes.
There are 3 rules. Electrons fill the orbitals starting with the lowest n and moving upwards. Second rule, no 2 electrons can fill 1 orbital with the same spin. If you're putting it in the suborbital, one has to be up, the other has to be down. For degenerative orbitals, the electrons fill each suborbital singly before any orbital gets a second electron, and they fill them with the same spin. So if I'm dealing with beryllium, beryllium has 4 electrons. My first 2 go into 1s, spin going up, spin going down. The second 2 go into the 2s, 1 going up, 1 going down. If I add boron, I have to employ the p suborbitals. Each one of the px, the py, and the pz, or -1, 0, and +1. Each one of these has the same energy level. So if you put this, instead of putting it in the far left one, if you put it in the middle one, I can't say you're wrong. Okay? But by convention, guys, start it with the far left first. So if that's where boron is. Now, I have 3 possible diagrams for carbon. I'm putting, carbon has 6 electrons. The first two electrons go in the first, spin up, spin down. The second two go in the 2s, spin up, spin down. Now, I have three possible places I can put those two electrons. I can put one in the first orbital, another in the second orbital with the same spin. I can put both of them into the first suborbital, one with the spin up, one with the spin down. I can put one in the first orbital, spin up, one in the second orbital, spin down. Remember, Hundrel said, when suborbitals of equal energy are available, the lowest energy configuration has an atom with the maximum number of unpaired electrons with the same spin. So I have electrons. First thing, maximum number of unpaired electrons. So because this one has paired up some electrons, I know this is not the state that I want. The second half of this with parallel spins. Parallel spins meaning they're spinning in the same direction. So I know this one is out. So Ian, when I go to oxygen, when I go to nitrogen,
Okay.
I go to nitrogen. Where is my next electron going to be? Describe that next electron.
It would have a spin down, correct? Because up, down. Oh no, it would have a spin up.
You want the spins to be the same. So the spin's going to be up. And which orbital are you going to place that in? The 2px, the 2py, or the 2pz?
Would it be 2pz?
2pz. You want the maximum number of unpaired electrons.
Okay.
So when I get oxygen, I'm going to put the first three in, spin going up. Then I have to put one more electron in. At this point, I have to put one of the electron spins paired up with one of the electrons that's already in there. But when I put it in there, it has to be spin down. For fluorine, I put another one that goes into another orbital. Its spin goes down. And neon, I finally fill the other one up, the last orbital up with the spin going down. Questions on this?
No, I'm good.
So as the number of electrons in this orbitals increase, so does the repulsion between them. And this is why you get the 3D having a larger energy than the 4s. But it doesn't quite give it enough energy to put it above the 4p. So that's why these fill a little bit funkily, if funkily is a word. All right, if I'm filling out arsenic, I got to go all the way back here to find my, good, arsenic. If I'm doing arsenic and I'm doing the entire electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, no, 4p3. Did you follow how I did that, guys? So I have the electron configuration. If you do the electron configuration, it makes the orbitals so much easier. So when I'm filling in arsenic, 1s gets two, there's 2, 4, 10, 12, 18, 20, 33. There are 33 electrons. I put 2 in the 1s. I got 31 left. I put another 2 in the 2s. 29 left. 2p, each one of those gets filled up. 3s gets filled up. 3p gets filled up. 4s, 3d. Then I have 3 electrons left. P's have 3 orbitals. So I put them in one at a time in each one of the orbitals with the spin going in the same direction. Are we good, guys?
Yeah.
If we're so good, what's the element? Remember what I told you when you're identifying the configuration. You can do the same thing here. What is the last orbital that had electrons put in it?
Is it bromine?
I'm sorry. I got one more. I'm tired of going back and forth.
Is it bromine?
Yeah, yes, correct. It is bromine. Okay. Ian, you're so good. What's that one?
6p. Lead?
You're right. Now, understand, if I'm doing the Ds, if I have like 5d5 there, I'm doing the same thing I did with the Ps. Each one of these electrons is going to go in with the spin going up. For F, I would have to put 7 electrons with the spin going up before I would fill in one of the orbitals with the spin going down.
So is that how we would determine if it's a positive or a negative 1/2? Is to spin up or down?
Yes,
on
I'm going to
that
show you,
chart?
Ian, I'm going to show you that. That's the next thing we're going to get into.
Oh, okay.
All right. Do I need to do this with you?
I'm good.
Ian or Gabe, you good with these?
Yeah, I'm good.
Yeah, I'm good.
Okay. Now, you do have some anomalies. This is what Jasmina was alluding to earlier. Okay. And that is if you can make a half-filled shell. If you can make a half-filled shell, it makes it more electronically stable. It decreases the energy if you fill half a shell with electrons. So you can sometimes accomplish this by pulling one of the electrons from the 4s orbital, because the energy levels are real close. Now, if I want to look at chromium, okay, if I was going to do the electron configuration normally with chromium, I would do the 4s2, 4s2, 3d4, correct? Guys, wouldn't that be what you would expect? 4s2, 3d4.
Yeah.
Well, these can hold 10 electrons. So if I have a possibility of half filling that shell, I'm going to promote one of the s electrons into the d. So instead of having one full orbital and one that's not quite half full, if I have 2 half-filled orbitals, this is going to make it more energetically sound, and so it's going to go into the 4s1, 3d5. Does that make sense to you? So if you want to mark chromium, molybdenum, tungsten, and I'm not even going to consider that because that's a made up element. Chromium, molybdenum, and tungsten will all promote one of the s electrons in there into the 3D. One of the 4s electrons goes into the 3D, 5s goes into the 4D, 6s goes into the 5D. Does that make sense to you? By the same token, if I have 9 electrons in the d orbital, I can promote one of the s's to make this a complete d shell. And that's what I'm going to do. So if I'm doing silver, silver's electron configuration, rather than being 5s2, 4d9, is going to be 5s1, 4d10. Gold would be 6s2, 4f14, 3d, 6s1, 4f14, 3d10. The only ones you really have to worry about are copper down to gold, chromium down to tungsten. That's what you're worried about. The same thing happens with the Fs, but I'm not going to do that to you. Okay. And the reason this happens is because the 3D and the 4s orbitals are so close in energy that it makes sense to do this. Okay. I'm just skipping ahead because this is something I need to get in before you leave for today. Conventionally, which means basically when I say conventionally, this is the way I'm dictating you to assign quantum numbers to the last electron. You have to understand that I can put it into any one of the 3 suborbitals in P, any one of the 5 for D, if I'm the first electron going in there. So I have to give you a convention for you to identify them from the quantum numbers I give you, or to identify the 4 quantum numbers from the last electron going into an element. Remember, n can be an integer up to 7. L can be n minus 1 down to 0, designated where it is in the periodic table. M sub L can be minus L through 0 to plus L in that order. In other words, when you're drawing the 5 suborbitals for D, I want you to put minus 2, fill that first. Minus 1, 0, plus 1, plus 2. That's the way I want you to fill the orbital D, the suborbitals in D. Does that make sense to you? I need to hear it from you.
Yeah.
All right. Now, when you're doing the M sub S's, if it's the first electron going into the suborbital, then I want you to call that a positive 1/2. If it's the second one going into that suborbital, call it a negative 1/2. Hopefully this will become clearer. And again, understand, barring any outside influence, such as the electron being in a magnetic field, there's no real difference in the M sub L or the M sub S quantum numbers. We're just doing this for convention's sake. Okay, if I have sulfur and I'm going to consider the last electron that is entered into sulfur. First thing I'm going to want to do is I'm going to want to draw. I'm going to either want to do an electron configuration and then an orbital diagram, or I'm going to draw the orbital diagram from scratch. The key is I need to know where that last electron, the orbital, that last electron is going in. I've done the electron configuration for sulfur. It's neon brackets 3s2, 3p4. So I know that my last electron had to go into the 3p orbital. So I've already defined two of my quantum numbers. The principal number is 3. The p designates that my L value is 1. Okay? Now I have to consider how the electrons were added into that p suborbital. Remember, I'm designating them as from the left to the right, -1, 0, +1. I have 4 electrons that go into that orbital. So the first 3 go in to -1, spin up, 0, spin up, +1, spin up. I now have to put that next electron. In reality, it could go into any of these 3. By my convention, I'm putting it into the -1 so that my M sub L value is going to go into the -1 suborbital as opposed to the 0 or the +1. Now, when I put it in there, is the suborbital occupied by an electron already? Yes. The first electron that gets put in there is a +1/2. So that my second one that goes in there is a -1/2. So my 4 numbers are principal, N is 3. L, because it's a p orbital, is a 1. My M sub L, it's the 4th electron going in. First one goes into -1, second one 0, third one +1. The 4th one is going to go into the -1. So my M sub L value for that electron is a -1. It's the second electron going into that suborbital. The first one was a +1/2, so the second one going in has to be a -1/2. Does that seem to make sense to you all?
Yeah.
Ian, Gabe?
Yes.
Yeah.
All right. For cobalt, I'm just going to draw. I'm just going to draw the orbital for the last 2 orbitals. So I'm not drawing the argons out. I'm just drawing the things from argon. Gabe,
Yeah.
what is my principal quantum number for the last electron going into cobalt?
Oh, wouldn't it be like half or -1/2?
No, principal quantum number,
Oh,
the
oh,
N
oh.
value.
2?
Okay, Gabe. Remember when we were doing electron configurations,
Yeah.
the first number stands for the shell or the principal quantum number. So where did the last electron go in? Did it go into the 4s or the 3d?
A 3D.
So what is the principal quantum number for 3d?
3.
3. Okay. Got one right. All right. Now, D is designated by, D gets designated by what the L value is. Do you remember what L is when we're dealing with D orbitals?
2.
2. So we got 3 is my principal, 2 is my M sub L. Okay, now we're going to my convention things. I've literally marked these. -2, -1, 0, +1, +2, Gabe, okay? Where did the last electron go in? The -2, the -1, the 0, the +1, or the +2?
Uh,
Okay, Gabe.
yeah.
Let me demonstrate again how these electrons fill the suborbitals. First ones always go in parallel spin. I want to make as many unpaired electrons as possible. So the
Right.
first ones all go in. The first 5 go in with the arrow up.
Mm-hmm.
I have 2 electrons left. Therefore, if I have 2 electrons left, they have to go into suborbitals with the spin going down. Does that make sense, Gabe?
Yes.
And I'm filling them from the left to the right. Understanding, I've marked this -2, -1, 0, 1, and 2. So the first extra electron goes in the -2 suborbital. The last electron goes into which orbital?
Uh, 1.
What sign?
Negative.
Because I've designated these -2, -1, 0, 1, and 2. So if the electron goes into this suborbital, that's designated as -1. So my M sub L value is a -1. Now, is there another electron in there, Gabe?
Yes.
So first electron in the suborbital has a M sub S as +1/2. So the second one going in there has a designation of
Negative.
-1/2. So if I'm looking at this, my 4 numbers are N is equal to 3 because it's going in the 3D orbital. L is equal to 2 because it's in a D orbital. I then draw out the 3D. I've got 7 electrons that go in there. First 5 go in, spin up. Next 2 go in, spin down. So this is the electron I'm talking about. I've designated the orbitals, -2, -1, 0, +1, +2. So it went into the M sub L suborbital -1. It was the second electron going in there. So the spin is a -1/2. Does that seem to make sense, Gabe?
Yeah. That makes sense.
Okay. Now we have to realize some things when we're given the quantum numbers, and I realize I'm going over, guys. When we're
Yeah,
given
I need to go for math class, so I'll watch the Zoom
okay,
when
Gabe,
you post it. Thank you, Professor. Have a good weekend.
you have a good weekend too, Gabe.
Thank you, you too.
Okay, when we're going from the quantum numbers, we can easily determine what the N and the L values are from the first 2 quantum numbers. N is always going to be whatever the first quantum number is. So I'm in the 4th shell. I got to look at the L value now. Remember, 0, if an L value is 0, it's S. If it is 1, it's a P. If my L value is 2, it's a D. So right now, I know I'm in the 4D suborbitals. Now, I got to draw the 5 orbitals out. Draw them in parallel to one another. I have to realize that my far left one is -2. Next one is a -1. I go 0, +1, +2. All right, Jasmina. I've designated my M sub S as being a +1/2. Does that mean it's the first or the second electron going into that suborbital?
The first.
The first. So that means I haven't paired up any electrons in there. So this means I have put one electron in the -2 with the spin going up, one electron in the -1 with the spin going up. So in other words, my 4D orbital has only 2 electrons in it. So I got to go back to my periodic table. See, this will work. So my 4Ds are right here, correct? Remember, 1, 2, 3, 4, 5s, 4Ds right below it. I only have 2 electrons going in there. 1, 2. What's the element, Jasmina?
Zirconium?
Zirconium. Does this make sense? Let's try one more. Actually, I went through it. Okay. Do you need some more help with that? All right, we're going to go through these. Do you both have a periodic table out?
Yes.
Yeah.
Jasmina? Okay. Find barium. Okay. So barium has a xenon shell. What is the rest of the electron configuration?
6s2.
6s2. Okay. So S's only have 1 suborbital. So draw one line there. I put 1 electron going in positive, 1 electron going in negative. Jasmina, what is the principal quantum number?
6.
Okay. S corresponds to what L value?
0.
Okay. Now, my M sub L. How many orbitals can there be? S
Just
has
one,
how
so
many
it's also
orbitals?
0.
Has to be
It's
0.
also 0.
If L is 0, M sub L has to be 0. So I've got that settled. Is it the first or second electron going in there?
Second.
So what's the M sub S?
-1/2.
Bingo. Ian, we're going to go down to, we've already done arsenic, I think. All right. Ian.
Yep.
There, Ian. All right. Arsenic. If I was doing the electron configuration of arsenic, where would my last 3 electrons go in?
4p3.
4p3. So how many suborbitals does a p have?
P2. No, P's 1.
P is 1, yes. So what's the principal quantum number, Ian? You just said 4p.
Yeah, 4.
4.
So n equals 4.
And L equals?
1.
1. Okay. Now, in p suborbitals, how many are there?
There's 3. There's 1, 0, and -1.
Other way around.
-1, 0, and 1.
Okay. And how many electrons are you going to put in these suborbitals?
3.
So do they go in? How do they go in?
Can you explain that? Sorry, I don't know why I got
Okay.
confused
Do
on
they
that.
go in 2 electrons in the first one spin up, 1 spin down, third electron going in.
Oh, spin up, spin down, spin up, spin down,
No,
spin
no,
up.
no, no, no.
Oh, up, down, up. So,
Nope.
or, okay. I'm
All
lost.
spins are in the same direction, Ian.
Got it.
So they all go in. So each of the orbitals is filled with 1 electron. They all have the spin going up.
Okay.
So Ian, our orbital designations, left, -1, 0, +1. Where was that last electron put in? Was it put into the -1, the 0, or the +1?
+1.
So my M sub L value is a +1.
So
Was
it'd
it
be
the first
positive
one?
1/2.
Was it the first one that go in there?
Yes.
So what's the last number?
Positive 1/2.
Jasmina, do you mind if I work with Ian for a second?
Yeah, I have another Zoom at 11, so I'm actually gonna hop off. I'm
Okay.
pretty good with this now.
You're pretty
so.
good with it? Because you
Yeah.
caught me in the error, I think you are. Okay.
Yeah, all right.
All right, Ian, it's just
Take
you and
care.
me then, all right?
Okay.
All right. I'm going to ask you, we're going to do silver.
Okay.
I want you, silver has start from the brackets krypton. I want you to do the abbreviated electron configuration for me. You got brackets krypton. What do you have then?
Okay. Brackets, krypton. So then it'd be 5s2, 4d. So it would be 49.
Or would it?
See, this is where I got confused. I got confused on this and then the last electron.
Okay. All right. Normally it would be 5s2, 4d9. Do you have the
Oh.
opportunity to fill that d orbital?
So it'd be 5s1, 4d10.
Yes.
Okay, I get
So
that
the
now.
last electron went into the 4d orbitals and it went into the d.
Okay.
All right. So Ian. Okay, Ian,
Yes.
4d10. What's the principle?
So it'd be 4 for n,
Go for it.
and then 2 for L.
All right, now draw the 5 lines. And you remember, you're starting from left to right, -1, -2, -1, 0, +1, +2.
Okay.
Are all the suborbitals filled?
Yes.
So the last one went into which M sub L?
2,
What kind of 2?
positive 2.
+2? Is it the first or second electron that went in there?
Second,
So what's the sign of M sub S?
negative.
There we go. Okay.
Got it.
You had to think through it, Ian, but you are getting it correct. And that was a hard one because you had to mess with the configuration as well. Now, this is a hard concept for people. But if I was going to give the same 4 quantum numbers for cadmium in,
Yes.
it would be the same. Okay? For cadmium,
Okay.
because I'm asking for the last electron. The
Mhm.
last electron is going into the same space for cadmium as it did for silver.
Oh, okay.
The difference is all you are doing is making sure that all the electrons going into cadmium have different quantum numbers than every other electron going into cadmium.
Okay.
They can
So would it-
have the same quantum numbers as like silver.
Okay. Would it be the same for like zinc and copper, for example?
Exactly. Exactly.
So all of those? Okay.
So
that makes a lot of sense then.
the quantum number going for the last electron going in would be the same for zinc as it is for copper.
Okay.
All right, now, please, Ian, practice these.
We'll do.
All right, I got one more set. We got to figure out the element from here. And I'm sorry for keeping you this late.
No, you're fine.
Okay. What is the element? All right, I'm going to show you how, I'm going to do the first one and show you how I dissect this, okay?
Okay.
I'm going to look at the first two. The first one is going to tell me I'm in the third shell. Okay?
Right.
The second one, the one, you're going to have to realize that that chart, S is equal to 0, P is equal to 1, D 2, F 3. If I've got an L value of 1, this means I'm dealing with a P orbital. So from the first two, I know I'm in the 3P. That means if you look at the periodic chart, I'm dealing anything from aluminum through argon. Does that make
What
sense?
was it again? S equals what? P for the orbitals?
Oh, I'm sorry, excuse me. S is equal to 0.
Uh-huh.
P is equal to 1.
Uh-huh.
D is equal to 2.
Uh-huh.
F is
And
equal
F
to
is equal
3.
Okay. I
There's-
have that written down.
Somewhere on in a previous slide, I said that.
Yeah, I
Okay.
didn't write it down. Thank you.
So what I'm doing when I'm looking at this, strategy wise, I'm looking at the first two numbers and I'm determining what orbital I'm in.
Mm-hmm.
Then what I'm going to do is I'm going to look over to the spin number. Because the spin number is the positive 1/2. Is that the first electron or the second electron going into that suborbital?
First.
First one. Okay. Then I keep that in the back of your mind. It's the first one. Then I look over. I look over to my M sub L value. And I
Okay.
draw them out. P's have how many suborbitals?
6
Nope.
or 3. My bad.
3 suborbitals. I'm going to label from left to right of those 3 suborbitals -1, 0, +1. Okay? So
Got it.
I'm going to look. First electron in, the last electron is in the +1. So if I'm entering them in, I have 1 electron going in the -1, 1 going in the 0,
Mhm.
1 going in the +1. +1 suborbital. Okay? So
Okay.
in effect, I've got 3 electrons. This is 3p3.
Mm-hmm.
I look at my periodic table. This has to be phosphorus.
Okay.
All right. Try the next one.
Okay, so it'd be in the second shell. And then 1 is equal to P. So it's 2P. And since it's 1, so it would be 0. Since it's 0, it's going to be -1/2. So is it fluorine?
Huh? Okay. Exactly.
Okay.
You feel pretty confident on this now?
Yeah,
Or do you
definitely
want,
after the Zoom.
or do you want me to go through this, go through another example?
Could you go through HG if you don't mind?
HG in terms of what?
Just going over it, just one more practice problem.
All right, tell me what you want me to do though. Do you want me to give you
Um,
the quantum numbers? Do you want the configuration, orbital diagram?
With the quantum numbers. So
Okay.
5, 2, plus
All right.
2.
So look at your columns. Okay.
Uh-huh.
So you're counting down. H is 1, Li 2, sodium 3, K is 4, RB is 5. When I'm on the HG level, I'm at CS, right?
Right.
So that's actually, see, when I begin that, that's the 6S, correct?
Correct.
Okay, 6S, then I'm getting into the Ds. What is the N for those Ds to the right of the 6S?
5D.
5D. Okay, so right now with the 5D, you got the first two quantum numbers. What is N?
5.
And the L is because of the D?
Oh, because it's a D, it's going to be 2.
2. Okay. All right. Now,
I get that now.
All
So
right.
L is equal to orbital based on. Got it.
okay. Now we have to deal with the M sub L. And again, when you're doing these, you have to at least draw the final orbital diagram for that last orbital that the electrons are going in, right?
Right.
So if you draw Ds, how many suborbitals are there in D?
10. So it'd be 5.
Nope. 10 electrons, 5. Yes. Okay. Sorry.
No, you're good. I just say
Okay.
extra words.
So you said it was 5D10, correct?
Correct.
So put the electrons in to each orbital, going up for the first 5, down for the second 5. Okay? So
Okay.
all the orbitals are filled with electrons, right?
Correct.
The last electron went in the far right one, correct?
Correct. So it'd be a negative then.
Nope. Well, it's a negative what, Ian?
M of S.
Yes. So now, second electron going in there, you know your M sub S is a negative 1/2. Now we have to figure out your M sub L. And remember, we're marking them from left to right, -2, -1, 0, +1, +2. So what's that
Okay.
last one go in?
2.
What kind?
Positive 2.
So your 4 numbers that you just determined were 5, 2, +2, -1/2.
Correct.
Okay?
Okay. And then I had a couple questions on